Yeah, hey everyone. My name is Shumo. I'm one of the core contributor of the Nebra labs. Today I'm going to show you the first protocol we're going to launch next week called Nebra UPA. Our goal here is to bring the ZK to the broadband age. So the first question we ask is like why we're building this, right? Why we're building UPA? Let's take a look at the ZK supply chain, right? If you think about that, the high level flow of ZK is that there is user want to prove something. Regardless, it's, hey, your private transfer, which is you need the input of your private key, or it's some kind of scaling operations. Either the scaling is Ethereum, or some like co-processors, or some like a ZK VM. Then they need to use a prover, and then they need to generate a proof and get a verifier. And one of the most useful verifier is that when you deploy the verifier on chain, so that it's publicly verifiable and it's trust, because the consensus layer will act as a trust mechanism, so that once you verify some fact on chain, everyone can trust that. So, and then if you dive a little bit deeper, there are two kind of paradigms. First is like for the privacy preserving applications. So note here, for the privacy preserving applications, or some people said it client side proving, because this is privacy sensitive, all the proving happens on the user side, which means either on their cell phone or in the browser. So basically the proving happens within the user's devices. And then the verification happens on chain. And then we have many kind of scaling solutions, for example, ZK rollup, ZK co-processors. The difference here is that usually users submit the data, for example, certain kind of transaction or certain kind of demand of proving something. And the prover, which is ZK rollup or ZK co-processors or some like a ZK ML solution, and this proof is generated in a very, very beefy server or some like server farm. And then at end of day, the proof is getting verified on chain, all right? So you can see here, the common interface is the verification on chain, right? Regardless of your like a ZK application or like a ZK scaling solution with kind of infra, everyone at end of day, you need to verify your proof on chain. So that's why we're building Nebra UPA to focus on the verification part, because that's a common interface and will become the cost bottleneck for people. Verification on chain is really, really expensive, right? I think there is a concept actually from Vitalik called proof singularity. The core idea here is that every single blockchain application will be a ZK application or proof-based application. If you think about that future is true, which I do, the biggest problem today is that the verification is very, very expensive. So these are the high-level picture of the verification costs in terms of both gas costs on Ethereum or EVM, and also the fiat costs in terms of dollar. So for example, for gross 16, the gas cost is roughly about 250K. Actually, depending on the size of public input, it could be even higher. The fiat cost is about like $20. And for the Halo 2 KZG, the fiat cost is about like $36. And for Stark Proof, it's actually even higher. So we recently talked to the Starkware team, right? So their Stark Proof is actually 6 million gas costs, is even higher for various reasons. So, but the high level takeaway here is that proof verification is very, very expensive. And we think this is the biggest bottleneck from ZK getting mass adoption. And this is also a famous quote from Vitalik. Like, do I want to buy like $20 to add privacy for my transaction to buy a coffee? Probably not, right? Like how many coffees, even in New York City, is more expensive than $20? So then we want to solve that. That's a goal of UPA. Next, I will tell you what is UPA, right? The idea, from the idea level, it's very simple. So basically we leverage the technique called proof aggregation. And proof aggregation, what I mean here is that we're generating proof of the proofs. In the sense that the Nebra UPA as a proof aggregator, we take various different proofs, and these proofs can come from different circuit and different parties. for example, one proof can come from a ZK VM, one proof can come from ZK rollup, one proof can come from like privacy preserving applications. And all these proofs are sending into UPA, and we generate the aggregated proof. It's a proof about these proofs. And then this proof can be getting verified on chain. So notice that during this entire process, like you don't have to trust us, because the aggregated proof will have the same kind of a cryptographic security guarantees in the normally you verify a proof on chain, right? So this is without needing to trust us. And as a result, right, because the cost of verify a single aggregated proof is roughly about the same as verify each individual proof, you get like cost amortization, and then you get like much higher throughput. And that's why we call it like a broadband ZK. And this can bring like a Ethereum ZK verification. We can scale Ethereum ZK verification about like 10 to 100x, and could be even more in the future. So I think one crucial aspect here is that we're not just building a protocol, we're also building a shared economy. In a sense, you can see here, there is no kind of a theoretical limitations of how many proofs you can pack into a single aggregated proof. And essentially, we're building the shared economy in the sense that the more proof you packed into a single proof, the better economy, right? So which means in the future, if we scale our like a proof aggregation pipeline and scale the computation power, getting more proof, the ZK proof is becoming cheaper and cheaper. And so here, this is a concrete gas saving right now for Nebra UPA can bring you. And this is our first generation Nebra UPA. So you can see, depending on the submission batch sizes, we already decrease the proof verification cost roughly 20x today. Please?
I'm curious, why is the total gas cost going up with the solution batch size? Or like, well, what's kind of the driving factor there?
Oh, so because the total gas cost, we don't not only like counting the aggregation proof verification, right? You need some like a metadata, you need a bunch of like S-load, EVM code, some data structures, Merkle trees, etc. Right? So we try to minimize the marginal cost per proof adding to batch, but that cannot be zero, for example. Yeah.
Okay.
Yeah.
Thank you.
So this is Nebra gas cost right now, right? So recently we have a very big customer talk to us. They have an insane amount of proof to verify, and this is a proof. This is a future, right? This is the L2 gas cost. You can see we can in the future, the TLDR here is that we can bring about 1.5K gas, which is about like 200x cheaper than the current Ethereum verification. I have five minutes to go. I do want to cover more of our product side of things. I will be very fast on the technical side, right? So UPA is permissionless, so which means we're a smart contract. Anyone can submit a proof, and also it's a censorship resistant and also progressively decentralizable. So we build on the current UPA 1.0, we're building on 2+ layer recursion in Halo 2 KZG. And underlying, we use a pipeline and distributed prover server architecture. So you can see we have, this is 2-layer of aggregation circuit, and each single circuit is actually running a GPU server, and these GPU servers can run at the same time. And also we use this pipeline approach, which means we're actually overlapping proving over batches to get maximum throughput. So for example, our current throughput is like 10 proofs per second, which means we can verify 1 million proof within like 1.5 days, which is more than the proof has been verified in Ethereum history. So here is a high level of UPA performance, right? So we compare naively just deploy a verifier on ZK VM. So you can see, because we are more specialized, we're about like a 23 to 40x faster than simply deploy a verifier on System SP1. We are about 60 to 140 times faster than simply deploy a verifier on RIS0. Okay, how you can use UPA? UPA is production ready today. We have already live in like a Sepolia for 3 months. So the first step is actually register your circuit. So we actually build this like SDK tools. You can do that from command line, or you can register that from like TypeScript SDK. Just register your circuit, and what you get is the circuit ID. And then this is the proof submission interface, right? You can see it's very simple. Basically, it's an on-chain API. You just submit your proofs with your circuit IDs and your call data. And your public input. And next, once your proof is verified, we actually build this proof explorer, right? Basically, you can see here, it's a proof batch, and we show you like, hey, your proof ID, your circuit ID, and some other things. Okay, so the next question is when UPA. So we're happy to announce UPA will be on Ethereum next week, so you can try it. UPA will be on the major L2s, so roughly like September, October. And we also are launching UPA 2.0 like later this year. Basically, we're using a ZK VM plus precompile architecture I mentioned before, right? If you're simply using ZK VM, that doesn't work so well. But we can incorporate our like a ZK proof verification circuit within the ZK VM and building as a precompile, so that this will bring support for all the proof systems. So happy to wrap the talk here. So I think previously I saw both Wei and David. So they're competing on the memes. So in the end, I have to bring a meme here. And so this is my meme. There's no meme. I love you guys. And this is my Telegram. If you want to verify proof on chain, let me check. Let's check. Yeah, thanks.
So my question about the performance, you mentioned that you can check the validity of the proof 10 proofs per second. What about the throughput? It's how you can also increase these values. Do you have any estimations on it?
Yeah, so 10 proofs per second is more like about the throughput, right? So
yeah,
it's like I think the current latency is about 3 minutes. So we can make it better by employing more like hardware acceleration and also. The first question is the throughput can be even further for more parallelization. And for the latency, so it's actually a trade-off between the proof size, the bigger proof size you have, inevitably you get like a longer latency. But under our current proof batch, like 32 proofs per batch, we can get like a much better latencies by improving across the stack. There are tons of low-hanging fruit here. For example, more hardware acceleration, and also like more efficient, like using something like a cycling curves to bouncing off the non-native arithmetics, and something also, for example, just like replace the Halo 2 with a more performant base layer proof system, for example, like Ligero, possibly. So I think there are many low-hanging fruit. We definitely will in the process of actually improving the latency as well. Yeah, thanks.